In 1907, the world was changed forever. The first plastic, Bakelite, was synthesised. In the 110 years since then, plastic has become a critical part of our society. We use it in everything, and it is amazing. It's used in clothing, in packaging, in transport, and even in medical equipment. And millions of lives have benefited due to the impacts of plastic. But there is a problem with it. You see, plastic is non-biodegradable. Sorry about that. Plastic is non-biodegradable, which means that it doesn't break down by itself, at least not easily. On screen here, you can see a monomer of plastic. This is the smallest particle that a certain plastic will break down into. It will reside in this particle for thousands of years. This particle cannot be used by most organisms, and it runs interference on a whole lot of organic processes that have to occur. So how big is this problem? It's pretty big. 16 times the weight of every human on this earth big. And it gets bigger, or rather it gets smaller. These statistics were taken from a study of marine organisms off the Belgian coast. And it was found at one certain location. The Pacific oyster and the blue mussel had 87 and 105 particles of plastic found in their tissues respectively. This was per 1 gram of tissue of these organisms. And because of the tiny size of these particles, a vast majority being less than 300 micrometers in length, these particles can actually be absorbed by our digestive tract, meaning that if you've ever eaten mussels or oysters from the Belgian coast, you have absorbed plastic. In fact, everybody in this room, thanks to our normal daily consumption of food, have absorbed plastic to some degree or another, and that is really disturbing because we don't even know how bad the effects of that can be. So how do we solve this? Well, we eat it. Not us, literally, but these guys and a few other organisms. Ideonella sakiaensis and mealworms have recently been discovered in the last couple of years to possess the capacity to break down plastics. Literally, they eat a plastic, they digest it, and they poo out organic compounds. That is awesome. How does that happen? In one word, enzymes. Enzymes are specialized proteins that increase the speed at which a reaction can occur. See, the reaction on screen right now is the same one that takes place in your outside world when breaking down the plastic PET. But here, it's shown with the action of the enzymes inside of the bacterium Ideonella sakiaensis. These two enzymes, PETase and MHETase, actually speed up this process. So instead of thousands of years, it now takes just a few hours. This sounds incredible. This sounds too good to be true, and unfortunately, it kind of is. You see, the initial reportings of these organisms had some flaws in them, and these papers were criticised at the peer review level. And so it's important we know why and how we can combat this. See, the reports were often criticised for overestimating any conclusions based off the results, and some were even criticised for not having results that would be applicable to everyday life. Their method of gathering data wasn't really open to everyday applications. What this means is that we can't really trust the conclusions coming from these papers. We need to be sure that what we're doing will work. But it doesn't actually mean that the data itself is wrong. It just means that it can only be used in certain circumstances. So, where are we now? Think of it this way. A mother has barged into the room of her teenage son and is sick of it. She's got a vacuum cleaner in one bag and a bin bag in the other, and she says, "Right, son, I'm sick of your mess. Here's a vacuum cleaner, here's a bin bag, now clean it up." Mother Nature has given us the vacuum cleaner and the bin bag. We've got to do the work to make them applicable. How do we do this? There are two schools of thought currently. One is that we improve the action of the proteins to make them more effective at their jobs and to essentially neutralise any of the problems that were found in the peer review section. And the other is to mass produce these proteins, based on the understanding that even if they aren't perfect, being able to apply them at huge quantities will still have a significant impact on the problems that we currently face. I myself strongly support the idea of mass production. The reason being that we can currently do it. Through a technology called plasmid recombination, we can take a DNA code for these proteins and then we can insert it into a piece of DNA that will then be inserted into millions of bacteria. And every single one of these bacteria will then be able to produce these proteins, these enzymes that we so dearly need. Look, this is not easy, but let me put it this way. This isn't some solution that's groovy and new to any old problem. This is the only viable solution that we have as a species to an issue that is threatening the stability of thousands of ecosystems around the world. If we don't act now, we will be acting too late. Look, this process will be tough, but let's break it down.